Okay, hello, welcome to our video. I'll be explaining the code portion of our project. Here is our Python file. Obviously, you start with your imports, and then we get into the important stuff. These are our variables that we're defining. As you can see here, we have a sample rate. That is the highest sample rate we can currently achieve with the analog devices ADR that we are using. And as I highlight here, you can see the different center frequencies that we will be analyzing or that we are analyzing. There are multiple of them, just so you can comment out one and kind of hot swap another in and run the program again. Here we're initializing our Pluto, which is the SDR that we're using with its IP address, and we're defining more variables in order to collect proper data for our experiment. Here we are creating, as where I'm highlighting, we are creating a 2D array to store different FFTs. It will be 100 rows long, or 100, yeah, it'll have 100 rows, and each row will have an FFT of size 100. And here's where all the actual work gets done in this for loop that I'm highlighting right here. So basically what we will be doing is we will be displaying, as I'm highlighting, 50 samples. Basically 50 different lines will be displayed on a graph, as you will see soon. And for each sample, we will be detecting 100 FFTs. And right now here, I'm setting the sample equal to the FFT. And I'm taking the length of the sample. This is just for debugging purposes. And here's where I'm actually putting the samples into the 2D array. Next, we need to do some more configuration here, such as FFT shifting and creating the magnitude and phase graphs for our experiment. Next, we will arrange our graph properly so that it properly fits the window. And then we will plot all of our samples in order in terms of the magnitude, the phase, and spectrogram. And in this whole for loop, what it's able to do, since everything's in a for loop, it will be constantly updating, as you can see next. And right now, I'll run the code with a sample rate of 61.25 megahertz and a center frequency of 2.4 gigahertz. And as you can see, we have our spectrogram, we have our phase and magnitude graphs respectively. And as you can see, they're all constantly updated. And Yael, would you want to start going over?
I could actually start, since it's Bluetooth. I could take the first one.
Sure thing.
Yeah. So the first center frequency, as Joseph mentioned, was 2.4 gigahertz, which is the Bluetooth range. And we believe this graph we're seeing is of Bluetooth for the reason in the physical layer of Bluetooth, we know that it operates using frequency hopping. In order to transmit data, it uses multiple frequencies quickly hopping between the two, and we're seeing various peaks in that range appearing quickly. So for that reason, we think that we've captured a Bluetooth signal here that we're looking at.
Okay. Moving on to our next center frequency. Right now, we will be displaying 462 megahertz. I'm sorry. Okay.
So at 462 megahertz, you will notice that there's a big hump. And this is actually a landline that is using TD ATM, or asynchronous time division multiplexing, which is basically taking your voice signal, creating a digital creating a digital application of your voice and splitting it up into different time sections to then be transmitted over air, so it's faster. So there's no time delay between when you send your voice signal to when someone is receiving your voice signal. And then at the receiver, or what we're seeing is that it is coming back and is getting multiplexed in this one frequency, which is at 462 megahertz.
We'll be now moving on to 698 megahertz. Oh, I apologize, I didn't save it properly. Okay.
So here we're actually looking at a television broadcast. We don't know which one it is, but we can obviously tell that it is a TV broadcast because of the huge spike that is occurring. And what the physical layer is doing is has an OFDM, which is an orthogonal frequency division multiplexing, which just creates low energy. It takes low power to just use the frequency and transmit the voice or what someone would be saying. And it's also using an MPEG to transmit the video. And that is what we are seeing in this location. And then there's also smaller humps next to it, which are other broadcasting. It could be television. Other networks are maybe using this, but they are unlicensed and they're not trying to take away from the main licensed broadcaster.
Okay, and next we'll be moving on to 1.4 gigahertz.
So for 1.4 megahertz, it is the same, or gigahertz. It is, if you look, it looks very similar to the 462 gigahertz that we were looking at beforehand because they're both landlines. So again, this is also using asynchronous time division multiplexing. And again, it is just trying to have the smallest delay between when you transmit your voice signal to when someone was to receive the voice signal.
It's kind of a pain to get out of this. And next, we will be going over the pagers channels or frequencies. And I do have a couple of pictures prepared here on my desktop. Here, you are able to see, I'm able to zoom in. This is what the final graph after 50 samples looked like while I was sitting next to UMass Memorial Hospital. As you can see, we have one big center spike, and then we have smaller spikes on flanking either side of the big spike. And as we have come to find out after testing that center frequency not around a hospital, these smaller spikes indicate that there is a lot of activity surrounding you or the data on Pluto, because there is a high amount of pagers currently active. And you can see that here, if say we uncomment this center frequency, while not being next to the hospital, obviously, there's a significant decrease in spikes surrounding our center spike, which proves to us that we are not intercepting any extra channels for pagers. Okay. And another important thing to note, or I can just run it again, something that we did not take note of yet, is our spectrogram or waterfall, I guess. And basically here, what you're seeing, if you can ignore the flashing of the different graphs, let me rearrange this. These different, and correct me if I'm wrong, Gail or Ryan, but these different colors, the shades represent different frequencies or channels and what the ADOM Pluto is intercepting. So for example, I think it was the lighter colors are stronger channels, whereas the darker colors are weaker channels. So the darker the graph is, the less activity there is surrounding your area in terms of the specific center frequency, obviously. So you can see that this graph is pretty, it's like half and half. So there is some and there isn't some activity. And for example, if we stop this and we go to, say, Bluetooth center frequency, what was the Bluetooth center frequency again? 2.4?
First one, yeah, 2.4.
Sure. We will most likely see a lighter graph. And the Bluetooth or the Pluto just disconnected. That's the end of our presentation. Let me reconnect it again. Hopefully,
Had to happen at least once.
you can skip ahead if you want in the video, but I'm reconnecting it. And this is a problem we've been having, Professor. It just disconnects whenever it wants. And it's been happening to multiple of us. So let's see if it reconnected. No, it did not. Okay.
It might have. No, it didn't.
Let me try again. Sometimes it gets it. Just wait. Okay, here it is.
Well,
Yeah.
Okay. Oh,
Yeah, it's not there anymore.